well known of all of your papers so far is on denoising diffusion probabilistic models, DDPM. That came out in 2020, and this paper laid the foundation for modern diffusion models, including DALL-E 2 and the first text to 3D models, like the kinds of things that you've been talking about so far at Genmo. So can you explain DDPM, these denoising diffusion probabilistic models, and how they relate to other kinds of approaches like generative adversarial networks, GANs, which were the way that people were generating images and videos primarily until recently. And perhaps, I realize I'm asking lots of questions here, but perhaps most importantly is tying all of this into stable diffusion, which people like are probably, many of our listeners are probably aware of in Midjourney. That's the approach that they use, and yeah, how it relates to your own work.
Yeah, I'm happy to talk about that DDPM project. Let me give a little bit of context to lay the landscape. So this was a paper that I worked on in 2019 and 2020, early in my PhD at Berkeley. I did my PhD with Peter Beal, who I believe has been on this podcast before.
Yes, indeed, yeah.
And I was very excited about the promise of generative models, but it felt like we had an incomplete picture, an incomplete set of tools, where it would take a lot of hand-holding, a lot of really careful tuning, data set curation, to even get something to barely work in visual generative media. Let me give an anecdote. So there was a project I was working on for in-painting, and the idea here was taking models like GPT that generate one word at a time, instead training them to generate one pixel at a time in an image. If you did that kind of thing, these models would only work at low resolution. And secondly, they wouldn't be able to do edits. They wouldn't be able to do something like replace, some object in an image. Let's say you have that vase with a handle on a table and you want to remove it, clean up the background. So even if we could train these visual models to generate one pixel at a time, they would work at, let's say, 32 by 32 pixels, little tiny, tiny images. But we wouldn't be able to use them for manipulations. So I did a project in that space where we tried to scale it up and we tried to make them more flexible at editing. We succeeded to some extent to both of those. But there seemed to be a hard limit where, to get to the interesting levels of resolution, like 256 by 256 pixel images, still pretty low resolution, but you can make out what's in the image. The model would take many minutes to sample an image because it's going one pixel at a time. You can kind of imagine as you scale up the resolution, you're quadratically expanding the amount of time it takes to generate that image. So compute became a problem. The second problem with using GPT-style models to generate images is that they would kind of become unstable and stop generating coherent content somewhere along the line. So if you're sampling thousands, tens of thousands, hundreds of thousands of pixels, the errors would accumulate where you would screw up one pixel, the model would sample something wrong. It's supposed to sample a blue pixel, but all of a sudden it samples a white pixel. That error would start to propagate. And the model would soon start losing the capability to understand what was going on and produce more of like a blurry mess. In addressing that computational challenge of tens of thousands of pixels, we asked the very obvious question of, can't we just generate multiple pixels simultaneously? GANs, generative adversarial networks, were able to do that. We started to work on Markov chain Monte Carlo, or MCMC samplers, that could in parallel synthesize all of these pixels. That project started to evolve over time into the Denoising Diffusion Probabilistic Models paper.
All right, nice. So yeah, so you're tackling this problem. You're realizing that maybe by predicting multiple pixels at once, you're going to get better results in single pixels at a time. You realize that Markov chain Monte Carlo, MCMC sampling, could be effective for that. Yeah. So how does that thing go on? How does that lead to this kind of stable diffusion approach?
Yeah. So once you start to sample multiple pixels at a time, the landscape is actually wide open for the architectures you can use. GPT-style models, these ones that generate one token, one pixel at a time, have some constraints in them. They are only allowed to look at the past, because if the model could look at the future, the rest of the pixels, the rest of the sentence, it would be able to cheat trivially, just repeat its input. And so you have to constrain the architecture. With DDPM, we realized that we could train a model which can see all the pixels simultaneously. But now there's another problem that how do we actually synthesize an image? So with our regressive model, it's clear. You generate one pixel at a time. You look at the past ones. You generate the next one. In DDPM, we have a slightly different architecture where you start with pure noise. So the image is all noise. And the question we ask is, if we learn a denoising autoencoder and an autoencoder that can look at this noisy image and strip out a little bit of noise, people use this for video processing and like fine-grained noise removal. Is that denoising autoencoder actually capable of generating an image, not just removing a little bit of noise? Turns out the answer is yes. We found this, my collaborator Jonathan Ho found this project from Joshua Soldikstein from 2015 called the Diffusion Probabilistic Models paper that builds a Markov chain that maps from Gaussian noise, then iteratively denoises it in order to produce a clean sample. There were a lot of architectural limitations in that diffusion probabilistic models paper from Joshua, that early work in 2015. It didn't produce that high quality samples. So in the DDPM project, we ended up making a lot of improvements to that framework, greatly simplifying it, changing the way we parameterize the model, coming up with new neural network architecture that worked a lot better. That neural network architecture is actually extremely similar to the architecture that Stable Diffusion uses. One of the key things we did was reweighting the loss function. And so not to get into too much technical detail, but essentially when you do this denoising process, it turns out that there's most of the things that people care about are high-level structure. What is the object? That there's an object kind of in the middle of the image. So I'm looking at you right now, John, on the screen. There's a person in the middle of the image. There's a guitar in the background. These are high-level semantic concepts. Those are most salient to people. And so part of what we did was reweight our loss so that would focus the model on learning these high-level things, denoising really high noise levels. So images that have extremely large amounts of noise in them, learning how to remove them. You might ask, removing noise from an image, how does that allow you to synthesize an image? The answer is, at sufficiently high noise levels, you actually need to fill in the missing content in order to remove noise. So let's say you have an image that is so noisy, you can barely make out what it is. You can kind of make out that there's a circle in the middle of the image. If you're able to actually strip out that noise, you're forced to learn what that circle might actually be, that it might be a face. So this formed the foundation for DDPM, where this insight that learning how to remove noise from an image could allow us to synthesize an image. A lot of that project was improving the architecture to make it actually happen, allow that model to learn this. Because in order to learn to denoise, you need to learn everything about what an image can look like, and that's hard to pack into a neural network. One of the interesting things that happened with that project is that it turned out to be a very stable loss function in the end. All you do is you take an image during training, you add noise, and you learn how to remove that noise.
Nice. Yeah. So this makes a huge amount of sense. This idea of iteratively removing noise while using a cost function that prioritizes the kind of salient objects in the image. And does this kind of stability, I'm wondering, this is something that I know nothing about. I'm mostly working in the natural language world, so like my machine vision stuff is relatively weak. Does this kind of stability help reduce hallucinations, or is that something that is a big issue in machine vision?
Yeah, so I think hallucinations are definitely a problem in visual synthesis. They take a slightly different form. So text in natural language is really dense on meaning. So there's stylistic things that it's coherent English. It abides by the grammar, right? So that's kind of what you might think about these low-level details visually. That objects aren't at the very ends of the color spectrum, super saturated. They may change smoothly. Images change smoothly. There are great sharp gradients around object boundaries. Those gradients are smooth, like a curve or a line. These are low-level things akin to the grammar of language. Right. These higher-level semantic concepts are what we start to notice when we talk about hallucinations. The model is saying things that are coherent English. It's perfect text, but it's incorrect, and it's just made up, right? Well, with a visual generative model, we have exactly the same problem. And oftentimes, it's actually a boon. A hallucination is a good thing because it allows people to create stuff that has never existed and never could exist in the real world. So fantastical combinations of two characters. We've seen people do mashups of animals and vehicles, so like a furry car or a bat swimming or some things like that. Um, People with their hair on fire to create incredible artistic effects. And so these are hallucinations in some sense that they don't exist, but they are what people want a lot of the time. So we need to build general purpose models that are able to generalize to those different semantic concepts. Another form of what might be called hallucination is that the model is getting some of these semantic ideas wrong, getting some of that grammar wrong. So let's say it generates, one thing we saw when we scaled up to high resolution faces is that the model would generate an eye with one color like blue and another eye with a different color like green. And so this can happen in reality, but in the vast majority of the training data, people have the same color eyes. And so the model is actually underfitting that distribution and hallucinating something that shouldn't be correct.
Very cool. I like that analogy between the grammar of natural language and the details of visual imagery. That makes a lot of sense to me at like an intuitive level. Awesome. Yeah, all the stable diffusion stuff, obviously making a huge impact in your own work, as well as in these kinds of popular tools like Midjourney. And it's wild to see how this is going to continue to get refined with the kinds of things that you're doing, these 3D representations, longer video. Really exciting, the area that you're working in. It must be really satisfying for you to kind of have a new architecture, and then you're like you probably hit your head on the wall, your team, for weeks or months at a time, sometimes trying to get like something to work, and then you finally crack it, and you're like, wow, you get these stunning, like this whole new level of visual capability. Yeah, you're really working in an exciting nexus of AI.
Yeah, it's been fascinating, and seeing this explosion of creativity that's been enabled by these models has been extremely satisfying. I'm very
Yeah,
happy
for
about it.
sure.
I think let me give one anecdote about
Yeah.
about this. So once we had identified some of these architectural building blocks that were really scalable, things were actually very easy to extend and to build in new settings. So here's an anecdote for that DDPM project. We built a model that could synthesize faces on the celebrity face data set. It generalized to more in the wild faces out of the box. These are things that GANs could do, though. GANs
Mhm.
like StyleGAN were able to synthesize high fidelity faces, even higher fidelity than we were doing. However, what they couldn't do is be able to be transferred out of the box to a new setting. They needed months of engineer time, tuning the hyperparameters, calibrating it. They were extremely unstable. What we did is we took that same model, same architecture, same loss, same hyperparameters, and just swapped the data set from 30,000 face images to 1.5 million images of different settings, like cats was one of the data sets. Another data set was churches. And another one, really interesting, was like a million image data set of bedrooms, Elsun bedrooms. And so
Oh
these are
yeah,
photos of
yeah.
the interior of people's bedrooms.
I've seen that even from years ago with like relatively early GANs, like in the
Mm-hmm.
first year or two of GANs. I remember that data set as being a really mind blowing moment for me because I could show like you could move through the latent space of the GAN that was creating these bedrooms, and it would like slowly shift the perspective on the bedroom or slowly change the color of the bedroom wall or yeah. And so that was actually one of the first, yeah, that data set was really important for me in realizing how crazy things were becoming in AI.
That's awesome. Yes, these latent space interpolations are so fascinating. They reveal some of the interior structure of the model, and I think it's also very humanistic because an interpolation is the first step to a video in some sense. Like a video is a very particular kind of interpolation, if you want
Right.
to look at it
Yeah,
like
it's
that.
like an interpolation over time.
Yeah, interpolation over time, where each frame is similar to the last one, but they change in a particular structured way. And so those
Mhm.
bedroom interpolations that you probably looked at, they don't change in these physically preserving ways. The conservation of mass is definitely not there. um, but one of the interesting things about the Elson dataset is that it started to generate photos of art on the walls. And so we generate
Oh.
these pictures of someone's bedroom, right? And people have art on their bedroom walls. That they purchase online and hang up. And so you could actually see in the model, the samples, there would be little pieces of artwork just hanging on the wall of someone's bedroom, sampled from the image. And this bedroom doesn't exist, that art doesn't exist, but it would be there in the image nonetheless. Uh, and the second thing that's really interesting is that that just worked out of the box, right? Same hyperparameters, it worked well enough. I did a little extra tuning. I doubled the model parameter count after we submitted the paper. So then in our rebuttal, when the reviewers come back with the critical feedback, you can say, oh, actually, we're now better than the GANs. We forgot to include that experiment.